This is my Calculus 1 course. Today we're going to learn some more volume and area problems. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In a previous class, we learned how to find the area between two graphs. And we learned that to find this area, we would have to use an integral with the difference of two functions, the two functions that are graphed inside the integral. And remember, if you don't want to get a negative area, then this function must be bigger than this function. The outputs of f must be bigger than the outputs of g from a to b. So this was a dx integral, which means that when you picture our rectangles that we're adding up, remember we're adding up an infinite number of rectangles, we considered the widths of these rectangles to be this horizontal lengths. So that's a dx integral. But sometimes it's convenient to use dy integrals in this situation, like we did in previous classes with volume. And in these situations, we're using rectangles where the widths are actually vertical dimensions. Now, in this situation, the heights of the rectangles are y values, or they're the difference of the y values, and the y values are written in terms of x. Okay, so again, that's a dx integral when inside the integral you have expressions in terms of x. But with a dy integral, everything's written in terms of y, but these outputs are actually they're actually x values. So this is kind of backwards. We don't really think of x values as outputs. They're the inputs in most cases. So when you're using a dy integral, you want to think of it in terms of subtracting x values. So we take these red x values, the distance from here to here, and we subtract the green x values, which is the distance from here to here, and that gives us the heights of our rectangles. So we're talking about x values. But again, the integral is written in terms of y, so the limits of integration are actually y values. Whereas over here with dx integrals, the limits of integration are x values. So this can be kind of confusing, kind of intimidating for students. But in the same way that we had three scenarios with our dx integrals, we have three scenarios with our dy integrals. You can look at those if you want, but the main thing to understand is you're taking the bigger x values, the red graph, and subtracting the smaller x values, the y graph, and that gives you the heights of all the infinite number of rectangles that we're adding up. So you have the situation where the red graph and the green graph are both producing positive x values. Then you have the second scenario where you have the red graph producing a positive x value, and then the green graphs are producing negative x values. Well, you still subtract the green x values from the red x values, and that gives you the heights of the rectangles again. That's why the formula works in all three of these scenarios. Then you have the situation where the red x values are negative and the green x values are also negative, but you still take the red x values and subtract the green x values, as you can see here. And when I say red, I'm talking about the f of x. So you're taking the f of x's and subtracting the g of x's in every one of these scenarios. So we're going to use dx and dy integrals, so you can get used to that. But the primary purpose for the area problems that we're about to do is to understand that sometimes you need multiple integrals to find the area of a region. Now we're going to start out with something basic that we've already done, and then we're going to show how sometimes we have to break this into, again, multiple integrals. But it says here, find the area bounded by the graphs of each set of equations using a dx integral. But then confirm your answer with a dy integral. So we can actually find the area of this yellow region here with a dx integral, and then we can also find it with a dy integral. So let's get started. So this is the same type of problem that we saw a couple classes ago, so there's nothing different here. So let's do a practice problem here. And by the way, I'm giving you this point. A lot of times you're not really given that point, you have to find it yourself. But if you did want to find it, all you would have to do is set this expression equal to this expression and then solve. But that would take some algebra and some time, and we don't really have, we don't want to spend a lot of time doing that, so I just gave you that point. And you can see this point with your own eyes. You can see that that's negative 3, 0. So we don't really need to worry about what that point is. But technically, you would have to set these equal to each other to confirm that those are the points. Okay, so we're going to take, or we're going to find the area, and this is going to be a dx integral, because it says to use a dx integral first up here. So what that means is our limits of integration are going to be x values. So we're going to start from negative 3, and then we're going to go to 2. So you see that 2 there, and the 3, or the negative 3. And we're going to take the top y values, which are 1/2 x plus 3/2, and then we're going to subtract the bottom x value. So this is the green graph, and then we're going to subtract the red graph. And the red graph is 1/2 x plus 1 squared plus 2. I'm changing the signs. Do you see how I changed the signs? It's not positive, it's now negative. And it's not negative, it's now positive. That's because I subtracted it. Okay, so let's now simplify. And there's a couple different ways you could do this. One way is you could actually just go ahead and expand that. The other way you can do it is you can just do a u substitution on this. You would actually need a u substitution to do that, but it's a pretty easy u substitution. So first let's add 3/2 and 2. Those are like terms. So that's going to be 5/2. And it seems like it would be a lot of work to have to expand that expression there, so I'm just going to leave it the way it is. Actually, that should be 7/2, I believe. Okay, so now we're ready to find the antiderivative. So we have 3/2 x plus 1/4 x squared minus 1/2 times. Now this is where you need a u substitution. You would let u equal x plus 1, but this is kind of an easy u substitution, so we don't really need to show all the u substitution stuff. So there you go, that is the antiderivative. You just add 1 to the exponent, but you have to counteract with 1/3. So you can confirm that that's correct by finding the derivative of all that. Again, if you want to stop and use a u substitution, you can do that if you want, but that's it's so easy that I don't think we really need to show all the U substitution, nor do we really have enough room to do that. Okay, so now we're going to plug in 2, so we have 7/2 times 2 plus 1/4 times 2 squared. Minus 1/6 times 2 plus 1 cubed minus 7/2 times -3 minus 1/4 times -3 squared. Then it's going to be plus 1/6 times -3 plus 1 cubed. And I think that's it. So we plugged in 2 over here, we plugged in -3 over here. So let's double check, make sure we did everything correctly, because it's very easy to make a mistake. And then you have to go back and do the whole thing over again. So you don't want to get in that situation. So everything looks correct that I can see. So we have 7 plus 1 minus 27 over 6 plus 21 over 2 minus 9 over 4 plus actually it's going to be minus, looks like minus 4 over 3. Okay, so I'm going to change this expression so that we have 42 over 4. That way we can combine these. And I'm going to reduce this expression so we have 9 over 2. Actually, I'm going to change this fraction so we have a 6 in the denominator, so we can combine. So I'm going to change that to 8 over 6. That'll just make the math easier for us. So we have 8 and negative 35 over 6, combining these. And combining these, looks like we have 33 over 4. Okay, so how many times is 6 going to 35? 5 times. And we have 5 left over. So just making the math a little easier with these mixed numbers. 4 goes into 33 8 times, with 1 left over. And so 8 minus 5 and 5/6 is 2 and 1/6. And continuing on here, looks like we're going to have 10. And if we add those two fractions together, we get 10 and 10/24. Actually, if we want to get a common denominator would be 12. So looks like that would be 10 and 5/12. So that is just some review. We've already done this type of stuff before. There's nothing really new about that. We found the integral of the the upper function, the green function in this case, the line, minus the lower function, the red function, the parabola. And that's how we find that area enclosed. But now we're going to do something a little different. Now we're going to calculate a dy integral. We're going to find the same area using a dy integral. And not only are we going to practice how to use a dy integral to find area, just as we practiced having to find the volume with a dy integral, but we're also going to learn that in some situations you have to use multiple integrals to find area. So let me show you what I mean. Instead of using rectangles like so with a dx integral, with a dy integral, and by the way, with a dx integral we integrated this way, but with a dx integral, or excuse me, with a dy integral, we're going to integrate using rectangles that are horizontal, so to speak. The heights of the rectangles are x values, or the differences between x values. But when we integrate, we're going to be using just the red graph on its own. But then when we get to here, all of a sudden something's going to change. Now we're not going to be using just the parabola. We're going to be using the parabola and the line. So we have to change when we get to that portion of the area, you see. So for example, if we're talking about this rectangle here, well, in order to calculate the height of that rectangle, the height in this case would be this length here, you would have to find this x value and then subtract this x value, and that would give you the total length there. This length plus this length. But when you get over here, in order to calculate the height of each rectangle, for example, this rectangle here, now you're using the red graph over here, but then when you subtract the x value of the green graph, well, obviously you're using a different function. You're not using just the parabola. You're using the parabola and the line. So you can't calculate this area using a dy integral. Just one dy integral. You have to use two dy integrals. All right. So we're going to integrate from y equals -2 to y equals 0. But then we're going to integrate from y equals 0 to y equals 2.5. We have to break it up into two integrals, or else we just can't do this. Now, remember, if you're using a dy integral, you have to solve for x. In both these equations, x is not solved for. So that's the first thing that we have to do. And again, we're doing two things here. We're learning how to use multiple integrals to calculate area, but we're also learning how to use dy integrals. So we're accomplishing many different things here. So I'm going to rewrite these, and I'm now going to solve for x. So we're going to subtract 3/2 from both sides. And actually, it's going to be a lot easier just to multiply both sides of this equation by 2. So we have 2y is equal to x plus 3, and then we can just subtract 3, and we get our x value there. Again, we need to have it solved for x. So now I'm going to add 2 to both sides, multiply both sides by 2. So we get 2 times y plus 2. And that's going to be square rooted. And whenever you square root both sides of an equation, you have to use a plus or minus symbol. Now, we could go through all the steps of how to solve for x, but that's really just basic algebra. Remember, you're expected to know the basic algebra before you enter calculus. So add 2 to both sides, multiply both sides by 2 to get rid of that fraction, square root both sides, and then subtract 1. And then you'll get this expression here. So now that's in terms of x. Okay, so these are the expressions that we needed. So now we're ready to go. So the area of that region that we're looking for, that yellow region, maybe I should use a different color for this stuff here. So the area of that yellow region is the integral from, and again, the limits of integration are y values now, so we're going from -2 to 0. And again, we subtract the bigger x value, which in this case would be this length, or we take the bigger x value and then we subtract the smaller x value, which would be this length. But notice that both x values are from the same curve. That's kind of weird. This is something that is very strange. That's because we have a plus or minus symbol here. X can be the positive, the version with positive root, or the version with negative root. So x is obviously going to be a bigger number when you have the positive version of this. When it's positive root, you're talking about this x value here. When it's negative root, you're talking about this x value. So what we're going to do is we're going to take the positive root and then we're going to subtract the negative root, and that's going to give us the sum of these two lengths, which is the actual height of the rectangle. And I'm offsetting those a little bit. So I know that that's kind of weird, but that's just what we have to do here. So it's going to be square root, and I'm going to go ahead and distribute. It'll make things a little easier. So we have square root 2y plus 4 minus 1. And then we're going to subtract the negative version of that. And again, it's going to be a dy integral. So again, we have the positive x value of the red graph, and then we have the positive version, positive root version, and then we're subtracting the negative root version because this x value is bigger than this x value. So again, I know that's kind of weird, but we're using the same graph on this part of the curve. Okay, so, but that's just the first part of the area. That's just from here to here. Now we need another integral to calculate the area from here to here. So that's going to be, again, the positive version of this expression, the positive root, and y is going to go from 0 to 2.5. 0 to 2.5. The limits of integration are y values. Okay, and we're taking the big x value and subtracting the bigger x value and subtracting the smaller x value. So again, we need root 2y plus 4, the positive root version, and then we're going to subtract the green graph, the line, the x value of the line, which is 2y minus 3. So we're subtracting 2y minus 3. So you see how we needed two integrals? We need this integral and we need this integral. Sometimes you have to do that when you're finding area. Okay, so now all we have to do is calculate the integral. So it looks like we're going to have 2 root 2y plus 4. And the 1's are actually going to cancel out. And looks like we have 2 minus 2y plus root 2y plus 4 dy. So there you go. That's our goal here, is to calculate these integrals. Now these integrals require substitution. So I'll write that over here. U would be 2y plus 4, looks like. And you can do that substitution yourself, but we can't really show that because that would just take too long to have to show the substitution. But let's change the form of this a little bit. So I'm going to take the 2 out. I just prefer to do that. And I'm going to change 2y plus root 2y plus 4 as 2y plus 4 to the 1/2 power. And same thing over here. You don't have to show this step. I mean, you can go faster through this. You don't have to wait for me if you know what you're doing. Okay, so let's find the antiderivative. You're going to add 1 to the exponent. So you're going to have 3/2, and then to counteract that, you need 2/3 there. But when you find the derivative of this, you have to use the chain rule. So you find the derivative of the outside function, you keep the inside function, and then you multiply by the derivative of the inside function. That's 2. So you have to multiply by the derivative of the blue expression. That's 2. And that would change this to, you'd have a 4 that would pop, or you'd have a 2 that would pop out here. You don't want that. So it looks like you need to counteract that with a 1/2 somewhere. So I'm going to multiply by 1/2. And let's see if that works. So if we find the derivative of this in our heads, let's see if it works. And it looks like it does. So if you do have to show the substitution, that's fine. Go ahead and go through all the steps. And if you need to review how to do that, you can go back to the substitution class. But oftentimes you can do substitutions in your head. So now we have 2y minus y squared plus same thing here. Looks like we're going to have 1/3 2y plus 4 to 3/2. And that is integrated from 0 to 2.5. So I know this is a lot of work, but you don't have to take this long. Like I said, you can go a lot faster through this. Okay, so we have 2 and then subtract 1/3. So I think we got that all right. I need my exponent. And then we're going to plug in 2.5 here. And then we just need to plug in 0. So you can do this as fast as you want. You don't have to show every step, like I said. We have minus 2 times 0 plus 0 squared minus 1/3 times 2 times 0 plus 4 to the 3/2. So I think I may have to make this a thinner pen so I can fit this on the page. Hopefully you can still see that. Okay. So you can do this on your own. I mean, it's really hard to show every step of this because it would just go on forever. But that becomes 8/3, and that becomes 0. Then we have 5 minus 6.25, and 9, it looks like. Then we have minus 8/3. Okay, so if we did this correctly, we should get 10 and 5/12. So we'll see what happens here. So then we get 16/3. So put all these together, and we've got 7.75. And then we've got 8/3 plus 7.75, which is the same as 2 2/3 plus 7 3/4. So then we have 9 and 17/12. And this fraction here is 1 5/12, so that becomes 10 5/12, which is the same thing that we got here. So you can see that in some cases we can use a dx integral and a dy integral to find the answer. Now, of course, in this case, the dx integral is much easier, so why would we use a dy integral? Well, again, 2 reasons. Number one, we need to learn how to do it, because in some situations it's actually going to be easier. You'll find as we do other problems today, in some situations it's going to be easier to use a dy integral. And also you need to know how to find area using multiple integrals. Okay, so again, we got the same area with a dx integral and a dy integral. So now let's try one more of these before you try one on your own. So we want to find this area, this yellow area here, enclosed by all these graphs. And when we use a dx integral, our rectangles are going to look like this. And we're going to integrate from here to here using the red and the purple graph. But then notice what happens when we change to this region. Well, now we're just using the 2 purple graphs. So we need to use a different integral. And then when we get to here, we're using the purple graph and the green graph. So if we want to find that area using a dx integral, we have to actually use 3 different integrals. So it's kind of weird. Now, if we're going to use a dx integral, we have to solve for y. And y is solved for with this equation, but it's not solved for with that equation. So if we solve for y, you see y is equal to plus or minus the square root of negative x. So that's kind of a weird thing there. We had to write a plus or minus symbol, and we have a negative inside the root. So that's very strange. But again, I just solved for y in this equation. I wrote the plus and the minus, although we may not need both, the plus and the minus. If you're using this bottom part of the red graph, you need the minus symbol here. If you're using the top part, you need the positive symbol. So we're going to be using the negative symbol, obviously, this part down here. Okay, so that said, let's get started. The area is equal to the integral from -4 to -1. How do I know that? Because x is -4 here, and then it's -1 here. That's where we're going to change to a different integral right there. And we're taking the red graph, which is going to be negative root negative x. Again, I know that's very confusing. We're taking the y value of this graph and subtracting the y value of that graph. Remember, you subtract the y values when you're using a dx integral. And then we're going to subtract the y value of this purple graph, which is -3. Alright, so that is the area from here to here. And we need to write our ornament there. So now we have to add the area from here to here. Now, to be honest, we don't really need an integral because that's just going to be a rectangle. I mean, we can just use length times height. That's just going to be 4, right? 1, 2, 3, 4. We can even see the squares inside there. Area is just adding up a bunch of square units, right? So we're going to integrate in this part, and the bounds are going to be x equals -1 to x equals 1. And we're going to take the upper y value, which is -1, and subtract the lower value, which is -3. Again, we're in dx integrals, we're talking about y values, so we're subtracting those y values. And they're constants because it's just horizontal lines. Then we're going to add the integral from 1 to 3, x equals 1 to x equals 3. And we don't really need calculus for this because that's just a triangle. It's just going to be 1/2 base times height, 1/2 base times height. So that should just end up being 2 for that. The area should be 2 for that triangle. But on that part, using calculus, we're going to take the y value of the green graph, which is -x, and then we're going to subtract the y value of the purple graph down here, which is -3. So there you go. As you can see, we needed 3 integrals. So just to be clear, this integral here is the area from here to here. This integral is the area from here to here, and this integral is the area from there to there. And we're taking the bigger y values and subtracting the smaller y values. Okay, so let's see what we can do. So I'm going to change that to -x to the 1/2 and plus 3. And I'm going to change this to, that would just be 2. And this I'm going to change to negative x plus 3. And now we're ready to integrate. Now this actually requires a u substitution technically. But it's such an easy u substitution that you can probably do it in your head. U would be negative x in that situation. Now a lot of students would say, well, wait a second, we can just multiply these negatives. Well, actually you can't, because the negative is captured in this exponential expression. You have to follow order of operations. Order of operations tells us to raise to the 1/2, then multiply by that negative, and you can't raise to 1/2 because we don't know what we're raising. It's just a variable. So just like we did before, I'm going to add 1 to the exponent, and then I'm going to counteract that by writing a 2/3 here. And I also have to consider the chain rule, because the negative is going to come out, so I guess I'll just take that negative away to counteract. So I think that should be it. Again, you can use the substitution principle. You can use substitution if you want, but you can also just do it in your head. So I think that's correct. And then we have to take the antiderivative of 3, which is 3x, negative 4 to negative 1. Okay, and the antiderivative of 2 is obviously just 2x. And the antiderivative of that is going to be 1/2 x squared. And then 3x going from 1 to 3. Okay. So remember, you have to make this the square root of x, or of square root of negative x squared. That's kind of a lot of work to do. So I don't know if I have room or the time to do all that work and show it for you, but remember, this is the square root of negative x cubed. Square root of negative x cubed. That's what that means. So make sure you understand that when you're trying to do your calculations, or else you're not going to go very far. That should actually be negative 3. And then we're going to subtract looks like it's going to be 16 over 3, and that's going to be plus 12. And here we have 2 minus 2, actually plus 2. And here we have, so that should be 4, because remember, that's just the area of a square there. 2 by 2 square. And then here we should get 2 for the area of the triangle, remember that? So that's going to be 9/2 plus 9, negative 9/2 plus 9, plus 1/2 minus 3. So we just have to add all this stuff together. So I'm going up here. So 2/3 minus 16/3 is negative 14/3. And we have negative 3 plus 12 is 9. And then 11, 13, 22, and 19. So add those up, we get 19. And then negative 9/2 plus 1/2 is negative 8/2, which is negative 4. And So then we have negative 4 2/3 plus 15. So that would be 10 1/3 looks like it's going to be. Okay, so again, sometimes you can't find area with one integral. You have to use multiple integrals. Now, I would not use an integral for this part and this part. I would just use basic formulas, length times width for the square, and then 1/2 base times height for the triangle, because it's just easier to do it that way. But again, I just want to demonstrate that using integrals, you're going to find the same answers. But now we're going to use a dy integral. We're going to calculate the same area using a dy integral, and you're going to find that a dy integral is actually going to be easier in the sense that you only need 2 integrals. Over here you needed 3 integrals with a dx integral, but for a dy integral you're only going to need 2, and here's why. You're going to be integrating from here to here, which uses the green x values and the orange x values. So we're going to integrate from here to here, but then you see we're going to change to the green graph and the red graph. But we only need to change once. So we only need 2 integrals. So using a dy integral might actually be easier. Now we do have to solve for x. Technically, x is already solved for in this equation, so we don't need to worry about that. But here we have to solve for x. So x is equal to negative y. Alright, so now we're ready to set up our integral. So we're going to integrate from y equals negative 3 to y equals negative 2. And we're going to take this x value from the green graph and subtract this x value. So the green graph is going to be negative y. Again, we have to have x solved for, so we have negative y, and then we're going to subtract the orange graph, which is negative 4. So that's the first integral. And then we're going to integrate from negative 2 to negative 1. So negative 2 to negative 1. And that's going to be the green graph, which is the line, negative y, that x value, minus the x value of the red graph, which is negative y squared. And so that's it. We should get the same answer. We should get 10 1/3 when we do this. We have negative y plus 4 and negative y plus y squared. So let's integrate. So we have negative 1/2 y squared plus 4y from negative 3 to negative 2, and negative 1/2 y squared plus 1/3 y cubed from negative 2 to negative 1. So let's start plugging things in. Then we'll go to this part here. we have minus 1/3 negative 2 to the third power. So we get 1 minus 8 minus 9/2 plus 12 minus 1/2 minus 1/3 plus 2 plus 8/3. Okay, so we can combine these two, and looks like we get 7/3, or 2 1/3 if you want to change it to a mixed number. And then we can combine these numbers. We have 1 minus 8 is negative 7, plus 12 is 5, plus 2 is 7. So we have 7. And then combining these, we have negative 10/2, and that would be negative 5. So we end up with 4 1/3, which is not even close to what we need. So that's to be expected. And looks like I forgot to put a 2 there on the exponent. So sorry about that. So we get negative 2 minus 8 plus 9/2 plus 12 minus 1/2 minus 1/3 plus 2 plus 8/3, it looks like. So then we get 7/3 and 4 and negative 10 plus 12 is 2 plus 2 is 4. And then we get looks like 10 1/3. So as you can see, we got the same answer that we did up here. So we used a dx integral, we used a dy integral, we got the same answer. Over here we had to use 3 integrals, over here we had to use 2 integrals. So you can see that there's all kinds of different situations. The dy integral in this case, it looked like that was a little easier. But again, we didn't even need integrals on the triangle and the square. So be aware that you don't really necessarily have to use an integral in some cases. Okay, so I want you to take a picture of this information here and this first problem that we did, and this second problem that we did. And I want you to try number 3. So you're going to calculate the area of the shaded region using a dx integral, and then you're going to calculate the area of that shaded region using a dy integral. And this can be kind of confusing, so try your best. When using a dx integral, remember you have to solve for y. So when you solve for y, you're also going to need to know, and we'll just go ahead and solve for y for you there. So when you solve for y, you're going to have plus or minus root x. You're going to need to know if you're going to use the positive root x or the negative root x. And So with this problem here, you're going to be integrating this area using a dx integral, but you're going to have to use both the positive root x and the negative root x. So you're going to have to take positive root x and then subtract negative root x to find the heights of the rectangles along here. Then you're going to have to change integrals to do this part. So it is going to be a challenge. So again, you can use the previous problems to help you. So get a picture of those and go ahead and try number 3. Do the dx integral part, and then we can check your answer, and then you can try the dy integral part. So first try the dx integral, and when you come back, we'll do it together. Remember, it's going to be this y value minus this y value, or this y value minus this y value. So try number 3. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, so I know this can be kind of confusing. It really can be confusing because it's hard to understand how these integrals work when you're using a dx integral, a dy integral, breaking them into 2 parts. Your limits of integration, are they y values, are they x values? It gets kind of confusing. If you got the wrong answer, that's okay. Just go back and figure out what you did wrong. It takes some practice to get used to this. Now we're going to use a dy integral, and it's important that everything is solved in terms of x. So this equation here must be solved in terms of x. So we must have x is equal to 2 plus y. So be aware of that. Your limits of integration are going to be y values. So we're going to integrate from here to here, and in this case we actually don't need 2 integrals. We're just taking the green x value and subtracting the red x value, and so we actually don't need 2 integrals. So go ahead and try your dy integral. You're going to integrate from y equals -1 to y equals 2. So see what you can do. When you come back, we'll do it together. Okay, we're back. So we got the same answer. So if you got 4 1/2, good. If you made a mistake, just go back and figure out what you did wrong. So with this integral, we're technically using x values. We have this, you see this orange x value, that's x. That's the x value of the green graph, and you're subtracting the x value of the red graph. Over here, we're using y values. You have the y value of the red graph, and then you're subtracting the smaller y value of the red graph. Over here, you're taking the y value of the red graph and subtracting the y value of the green graph. But the limits of integration over here are x values, whereas the limits of integration over here are y values. So these limits here. So it's very confusing. But if you got that right, good. So go ahead and take a picture of that, and you can use that to help you with number 4. Again, if you haven't gotten a picture of all this information, I'm going to give you one more chance to do that. We have this problem that we did so far. We have this problem, and we have this problem. So go ahead and try number 4. Start with the dx integral. So everything is solved for in terms of y, or it's written in terms of x, but y is solved for, so you don't have to do that. So what we're going to be doing is we're going to be integrating from 0 to 2 using the green graph and the red graph, but then we're going to change to the green graph and the orange graph, so we need 2 integrals. So go ahead and try number 4. When you come back, we'll do it together. Okay, we're back. 7 and 5, 6. Okay, so if you got that right, excellent. So we had to use two integrals there. Now we're going to use a dy integral. So we're going to need three integrals for this. We're going to integrate from y equals -2 to 0 using the purple graph and the red graph. Then we're going to integrate from 0, y equals 0 to y equals 1 using the two purple graphs. And then we're going to integrate from y equals 1 to y equals 2 using the green and the purple graph. So you need to solve for x in all the equations. So very, very important that you start by doing that. Now you're going to need a u substitution. U is going to be -2y, so this might be a challenge. So do your best. See what you can do. When you come back, we'll do it together. Okay, we're back. 7 and 5, 6. So as you can see, we got the same answer. So if you got that right, good. Now that was a challenging problem. There's u substitutions and all kinds of weird things going on. But if you got that right, excellent. A lot of students have problems with this. They have trouble with this because it's very confusing. So don't worry if you're having a little trouble with this. It's kind of a lot of convoluted stuff. You have x values and the limits of integration. You have y values and limits of integration. You have you're subtracting x values from x values. Sometimes you're subtracting y values from y values. It takes a while to get used to this, how this works. So if you're having a little trouble with this, that's okay. In previous classes, we found the volume of a solid of revolution. But now we're going to find volumes of solids that are not solids of revolution. So that's the difference here. So let's do an example. Remember, we learned that f of x is, if it's the heights of rectangles, then the integral of f of x gives us a number representing area. And if a of x is the areas of cross-sections, then the integral of a of x gives us a number representing volume. So we're going to use this principle. It's just that we're not referring to solids of revolution, we're referring to other types of solids. So let's do an example. The base of a solid is the graph of the relation x squared plus y squared equals 4. And if you don't remember, that's actually a circle. The cross-sections of the solid perpendicular to the x-axis are squares. Find the volume of the solid. Now, it's a lot better to say parallel to the y-axis than perpendicular to the x-axis, but on the advanced placement test, they're going to do things like that just to confuse you, so I'm just getting you used to that. So let's draw a picture of the base of this solid. And I'm going to use something to draw the shape. So we have a circle. Now, in case you don't remember, the standard form of a circle is x minus h squared plus y minus k squared equals r squared. And what we have here is x minus 0 squared plus y minus 0 squared is equal to 2 squared. That's this equation up here. So the radius of the circle is 2. That point, for example, is 2, 0. So this is the base of the solid. It says cross sections of the solid perpendicular to the x-axis are squares. So what this means is you have a square. If you cut this solid parallel to the y-axis, then the bottom of the square is that purple line, and then the shape is actually going to come out of the page. And it's kind of hard to draw that, but just picture this part actually coming out of the page. It doesn't really have to. It's just coincidental that it's hitting that point there. It doesn't really have to, but so picture that square coming out of the page. So what we're going to do is we're going to find the area of this square and an infinite number of other squares, add them all up, and then we have the volume of the solid. Now, I know what a lot of you are going to think. You're going to think, well, what does that solid look like? Well, we could figure it out if you wanted to, but we don't really need to. So let's find the volume. It's the integral of the cross-sectional area. And before we do that, what we're going to do is we're going to find this orange y value, this y value here, and then we're going to double that y value, and that will give us the base of this square. Then we're going to find the area, and this length is the same as this length because it's a square, so we're going to multiply that expression by itself, and that'll be the area of each square. So again, this orange length is what we're looking for. So in order to find that, we have to solve for y in this equation here. So y is equal to plus or minus the square root of 4 minus x squared. Alright, so what we're going to do is we're going to take this value, which is positive square root 4 minus x squared, and we're going to subtract this pink x value, which is negative square root 4 minus x squared. And that gives us that overall green length there. That's what we want. That's the base of the square. Okay, so square root 4 minus x squared minus negative square root 4 minus x squared dx. And before I do the integral, I should probably find the parts here first. So we'll just call this, you can call it the width, you can call it the base, it doesn't really matter. I'm gonna put a big W there for width. Okay, so the width is 2 times root 4 minus x squared. Because it's a double negative, it becomes positive, you add it together, you get 2 of those. Okay, now the length, let's do the length now. What color should we make that? I guess blue. I'm running out of colors. We'll make this the length. So the length is equal to the same thing, because it's a square, right? If the width is this length, then the length must be that length also. It's a square. So now the volume is the integral of 2 root 4 minus x squared, which is the width, times the length, which happens to be the same thing. Remember, the area is a function of x. Oh, we don't have to write it as a function of x now, but area is length times width. And if you want to write it as a function of x, we would write it as 2 root 4 minus x squared times 2 root 4 minus x squared. So now we're putting it in the integral. We're going to add up. Now again, look at this. We have the cross-sectional area in the integral. So we put that cross-sectional area in the integral, and we want to integrate from x equals -2 to x equals 2. All right. So we multiply these 2's together, we get 4. And I'm going to go ahead and put that on the outside of the integral. When we multiply these roots together, we're just going to get rid of the roots. We're left with 4 minus x squared. Okay, so now we can integrate, and we get 4x minus 1/3 x cubed from -2 to 2. So plugging in 2. And subtracting the same expression with -2 plugged in. And so it looks like we get 4 times 8 minus 8/3. Plus 8 minus 8/3. Let me find some more room here. So we get 128 over 3. So again, that was not a solid of revolution. That's the difference here. So you can look that over if you want. We had cross sections that were squares. Let's try another one. It says the region bounded by y equals x squared and y equals -x squared plus 8 is the base of a solid. Cross sections parallel to the y-axis are isosceles right triangles. Cross sections parallel to the y-axis are isosceles right triangles, and the base of each triangle is the hypotenuse. Find the volume of the solid. Okay. So let's draw the base of the solid. So we have y equals x squared, which is going to look something like this, and we have y equals -8x squared, which is going to look something like this. And so the region bounded by those graphs is this region here. Now cross sections parallel to the y-axis are isosceles right triangles, and the base of each triangle is the hypotenuse. So if something's an isosceles right triangle, that means it has to be a 45, 90 degree triangle, because we know this angle is 90, and we know there's only 90 degrees left because of the triangle sum theorem tells us that all the angles add up to 180. And if these angles are the same, that means each one must be 45 degrees. And we're told that the base of the triangles is this length here. So if we take a little sliver there, our triangles are going to look something like that. Maybe I'll move it over a little bit. Move it over here. So picture this part coming out of the screen. Okay, that's what we're dealing with here. And what I'm going to do is I'm going to flip that triangle around so that its hypotenuse is the base. I can give you a better idea of what's going on here. Okay, so we need to know the areas of those triangles. First of all, we need to find this length here. And I'm going to color this a special color because I want to make sure that we're all on the same page here. So how do you find that purple length? Well, what you do is you take the y value of the blue graph. I'm going to call this b for base. The y value of the blue graph is negative x squared plus 8. And you subtract the y value of the red graph. It's that simple. So we have negative 2x squared plus 8. That's the base of that triangle. And the reason we need that is because the area of a triangle is 1/2 base times height. We need to find the area of the cross sections and then add them all up with an integral and we get the volume. But we need to know how to find the area of the triangles because those are the cross sections, the triangles. So we found the base in terms of x, but we need the height. Well, the height is this this orange distance here. But how do we find that? Well, it turns out when you take this triangle and set it on its hypotenuse and draw the altitude, you just create two other 45, 45, 90 degree triangles, because this angle is 90. As you can imagine, if you cut it in half, then you're going to be left with 45 degree angles here. Alright, so this green length here, I'm going to draw it down here, that's 1/2 of the purple length, right? But that green length is the same as the orange length. In fact, I'm just going to make it the same color because, again, this triangle here is a 45, 45, 90, which means that the legs of the triangle are the same. So if we can find this orange length, we can find the height of the triangle, but the orange length is just half. It's just half the length of the base. So that would be negative 2x squared plus 8 divided by 2, which is negative x squared plus 4. So that's the height. So the area the area of the triangle is 1/2, and this is the area in terms of x, is 1/2 times the base times the height. Okay, and now we can factor out a 2 out of here. If you factor out a 2, that just gets rid of that 1/2. Or you can just multiply this 1/2 into this. Now, a lot of students, they'll say, well, we're going to multiply this 1/2 into this, and we're going to multiply it into this. It's a distribution rule. Well, no, that only works if you're adding the green expression and the blue expression. We're not adding them, we're multiplying. So anyway, long story short, we get negative x squared plus 4 times negative x squared plus 4. And we can expand that out, or we can just write it in in exponential form, but it's actually going to be easier to expand it. And if we use FOIL and add up the inner terms, we come up with the following expression. Okay, so the volume of the solid is the integral from x equals whatever this value is to x equals whatever that value is. We don't know what those values are, and we're stuck. We can't figure it out unless we set these two equations equal to each other to find the intersection points. So y1 equals y2, if you want to call it that. X squared is equal to negative x squared plus 8. And we don't have a lot of room to solve, but when you solve, you find that x is equal to plus or minus 2. Alright, so this x value is negative 2, this x value is positive 2. So we're going to integrate from negative 2 to 2. And the area of each triangle is given to us by that expression inside the integral, this green expression here. Now, there's one thing that I want to show you here that is very useful. You see how we're integrating from negative 2 to 2? But you can see that this yellow region is symmetric. It's symmetric about the y-axis. And so what that means is you can integrate this part here and just multiply by 2. Now, you don't have to do that, but it makes the math a lot easier. So I'm going to integrate from 0 to 2 and multiply by 2. Now, if that confuses you, you don't have to do it. But that's something that we have not talked about in my curriculum yet that I can remember. But that's just a trick that makes things a lot easier. So symmetric about the y-axis. That's why we can do that. Okay. So let's integrate. Integrating from 0 to 2. So we're going to plug in 2. And we're going to subtract same expression with 0 plugged in. And so let's see if we can do this. These are kind of big numbers. So we want to get a common denominator. So if we combine these two expressions, looks like we have negative 224 over 15. And 15 goes in 14 times. So it looks like we have negative 14. 14 fifteenths it looks like it's going to be. So let me find some more room. So it looks like we're going to end up with 34 and 2 fifteenths. Sorry, we're so scrunched in there. So again, another example of a solid that is not it's not rotated around anything. So I'm going to make the bases yellow on these problems. Don't really need to, but okay, let's try some more of these. It says here, the region bounded by y equals x, y equals 0, and x equals 2 is the base of a solid. Cross-sections parallel to the x-axis are semicircles. Find the volume of the solid. So, as usual, let's graph the base of the solid. We have y equals x. We have y equals 0. And we have x equals 2. So the base of the solid is this triangle region here, and we have cross sections that are semicircles. So picture this top part of that circle coming out of the screen. And I'm going to take that out here and make it a little bigger. So we need to add up the cross section areas, or put the cross section areas in an integral. So area of a circle is pi r squared, but we're finding the area of semicircles, so it's going to be 1/2 pi r squared. And because the cross sections are parallel to the x-axis, we're going to use a dy integral. So our integral is going to be written in terms of y. So we're going to have 1/2 pi r squared, but what is r? R is this distance here. But first we're going to find the diameter of the semicircle and then divide that by 2. So we're going to take this x value, which is 2, and then we're going to subtract this x value, which is y. Now, how do I know that's y? Because if you write x in terms of y, of that green line, it's just going to be y. So the diameter of the semicircle is 2 minus y. Okay, so 2 minus y is diameter, and the radius is going to be half that. Okay, so now we're ready to write our cross-section area function. We can write it here, I guess. So 1 minus 1/2 y squared. And we're ready to find the volume. Now y goes from 0 to whatever this point would be. Now obviously the orange graph tells us x is 2, but if x is 2 in this equation, then y must be 2. So y is going from 0 to 2. And again, this is a dy integral. Okay, so I like to take the constants out, if I can, the constant multipliers, and I'm going to expand because it's going to be easier to integrate if we expand. You don't have to expand, but you'd have to use a u substitution if you didn't expand. Okay, so now we're ready to integrate. So it's going to be y minus 1/2 y squared plus 1/12 y cubed from 0 to 2. So now we have 2 minus 1/2 2 squared plus 1/12 2 cubed minus 0 plus 1/2 0 squared. You don't have to write all this. You can just understand that it's all going to go to 0. Okay, so let's do the math. So looks like we have 2 minus 2 plus 8/12. And all that stuff becomes 0, obviously. And these cancel out. 8/12 becomes 2/3. And 2/3 times pi over 2 is pi over 3. So there you go. So that was, we had to use a dy integral there. Okay, so let's do another problem where we have to use a dy integral. It says the base of a solid is the graph of the relation x squared plus 9y squared equals 9. The cross sections of the solid perpendicular to the y-axis are equilateral triangles. Find the volume of the solid. So let's graph the base of the solid. Now, you may not recognize that. It's been a while since we looked at stuff like that. But if you divide both sides of that equation by 9, it might get a little more familiar to you. If it's not more familiar, then let's write the standard form of an ellipse. So A is 3. What that means is we go out -3 and 3, and obviously we can see that K and H, they're not there, so we just consider those to be 0. And B is going to be 1, so that means we go up 1. So our ellipse is going to look something like that. Now it says cross sections are perpendicular to the y-axis, so we're going to have a cross section that looks something like this. And cross sections are equilateral triangles. So I'm going to draw a triangle like that. So we have to find the cross section area. So the area of a triangle is 1/2 base times height. And we're going to write this in terms of y, but we don't have the base and we don't have the height yet, so we have to find those things. So to find the base, we're going to use this equation here. So the base is going to be it's going to be this length times 2. Now we can solve for x in this equation, and that's going to give us that length, this length here. So if we solve for x in that red equation, we're going to get, well, that's not the base, that's half the base. We'll just say that that's equal to x. The base is equal to 2 times that. So the positive version of this, again, that's this length here, but if we double that, we get the whole length, the orange plus the purple. That's what we want. So so that's the base. 2 root 9 minus 9y squared. Now we need to find the height, so I'll make this purple distance the height. And how do we do that? Well, we'll take this triangle out, and we'll understand that this triangle is actually a 30, 60, 90 degree triangle. The reason for that is all the angles in a equilateral triangle are 60 degrees. If we cut this angle out at the top in half, we get a 30 degree angle. So let's take that triangle out, put it over here. That's that blue triangle. Now because this is a 30, 60, 90 degree triangle, remember the side opposite 30 we can call W, and the side opposite 60 we call W root 3. And this side is 2W, but we don't really need that. So W is going to be half of this length. So 2 root 9 minus 9y squared divided by 2. So that's just root 9 minus 9y squared. And the height of the triangle, well, that's going to be W, which is the expression we just found, times root 3. So 9 minus 9y squared times root 3. Okay. So now we have the height. And we'll make that height orange, I guess. So the height is root 3 times root 9 minus 9y squared. Okay, now I'm going to factor out 9 in that root to make things easier for us. Now, remember, we have two rules with roots. We have multiplication rule and division rule. This is the multiplication rule going backwards. If you multiply these two because they're roots, you can just multiply the insides and make them one root, right? So we're just going backwards there. So then we get root 27, or actually root 9 is just 3, so I can just make that 3 root 3. So that is the height. So now the area, the cross-section area as a function of y is 1/2 times the base times the height. And so now let's simplify that cross-section area expression. We get root 3 and then 9 minus 9y squared. When you multiply the roots go away because the expression inside the root is the same for both roots. And 2 times 1/2 is 1. So I'm going to pull out that 9. So we have 9 root 3 times 1 minus y squared. I think that would be easier. Okay, so that is the cross-section area. Now we're going to find the volume. That's going to be the integral from -1 to 1. Of 9 root 3 times 1 minus y squared dy. Now remember, we can do a trick. The trick is we can multiply by 2 and change the integral from 0 to 1, or from negative 1 to 1 to 0 to 1. And that'll make it easier for us to integrate. So I'm going to take out that constant. So we have 18 root 3 times the integral from 0 to 1 of 1 minus y squared. And then we're going to integrate. And we don't have a lot of room here, so looks like we're going to get 12 root 3. So there's another example of a dy integral problem. Okay, so I want you to take a picture of these two problems and take a picture of these two problems, and I want you to try number 9. Now, this problem up here is going to help you with number 9 because we have an ellipse. You see this equation, this green equation up here? Remember, that's an ellipse. In order to see how to graph the ellipse, you have to divide both sides of this equation by 4. This equation here. And so try number 9. When you come back, we'll do it together. Okay, we're back. 64 over 3. So there you go. If you got that right, excellent. Okay. So go ahead and try number 10. If you got number 9 right, good. When you're done with number 10, we'll do it together. Okay, we're back. So there you go. If you got that right, excellent. Now you could have kept your expression as x plus 3 squared, but then you would have to do a u substitution. The arithmetic would be a lot easier then, but you would have to use a u substitution. So if you got that right, excellent. Now get a picture of these two problems and try number 11. Now for 11, there's going to be a dy integral because your cross section is going to be perpendicular to the y-axis. And be aware that this here is going to be a circle centered at 0, 0, and the radius is going to be 4. So try number 11. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay. So go ahead and try number 12. And when you come back, we'll do it together. Okay, we're back. That's going to give us 32 over 3. So if you got that right, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and screenshot number 2 and number 3, 4, 5, 6, and 7, and 8, and 9, but don't go before you get your homework. Remember, the homework is not optional. It must be done completely and correctly and kept in order in your binder. So here's screenshot number 1 of the homework and screenshot number 2 and number 3 and 4. But don't go before you get the answers. It's not enough just to attempt the homework. It must be done correctly. So here are the answers. You only have 6 problems, as you can see. Now, for the first 2 problems, I want you to calculate these. I want you to calculate those with a dy integral and a dx integral. Now, technically, you can find the answer with just one method, but you need to get used to using dx integrals and dy integrals. So get that homework done, and I'll look forward to seeing you in the next class.